All right, in this next section, we're going to take a look at two different quantities, arc length and the surface area. So we'll put surface area on hold for a few moments, and we'll take a look at the arc length. So arc length is simply the actual distance of a curve. So if we go from the very beginning to the very end, the straight line distance, that would be the displacement. Just measure the distance from the very beginning directly to the very end. It's not the true distance traveled. Okay, so that would be displacement. If we want the actual distance traveled, that is what arc length is. So this, you can pause the video if you'd like. This walks through how we can approximate it and how we can essentially come up with an expression for this theorem for the arc length. Essentially what we do is, like all things in calculus, if we want to figure out an exact expression for something that varies continuously, what we do is we approximate it and assume that we approximate it in a way that we can calculate it. So we take this full curve and we split it up into some straight line segments. So although it is curving, we can approximate it with a straight line segment, and that distance will give us a good approximation provided we have split this interval up into sufficiently many little pieces. So essentially what we do is we find the distance of each piece and then we add up all of these distances. So the very reason why we have a square root in this arc length integral is because what is the distance formula? Well, distance formula is, of course, just the change in y squared plus the change in x squared minus x1. Okay. And we can see the derivation right here. We do start with the distance formula, and then there's some algebra that takes place which allows us to factor out this delta x squared, and using a limit and the idea of a Riemann sum, we can have this approach the expression that we have. But you do not have to, at least for any classes that I teach, you will not have to replicate this derivation most likely, certainly not for any classes I teach. But it is that idea in calculus is important to understand. So for us, arc length is going to be this integral. So it is the square root of 1 plus the derivative of the function squared. So let's go ahead and take a look at an example here. Determine the arc length of the natural log of the cosine of x over the interval 0 to pi over 4. Okay, well, what I would do is we know the arc length function, or the arc length integral from a to b, square root of 1 plus the derivative squared. Generally speaking, I find it easier to build the inside of the square root outside of the problem. So I will just begin by writing down the function, taking the derivative. So derivative is 1 over the inside times the derivative of the inside, which would be negative sine. So that becomes a negative sine of x over cosine of x, which of course is just negative tangent. So that's the derivative. So what I would do now is just square both sides to get tangent squared, and then I would of course just add 1 to each side. Line by line, we're building the inside of the square root. It's a lot easier to do this off to the side than to do it all within the integral itself. So tangent squared plus 1 is a trig identity. It's secant squared. So now that we have the inside of our square root figured out, we can even just say what that is going to be. Or we can go ahead and plug it all into the arc length integral at this point. Doesn't really matter. So that's what I'll do. So our bounds are going to be 0 to pi over 4, and we have secant squared of x as our integrand. This, of course, will simplify into the integral of secant. The integral of secant is a slightly complicated integral. This is something you're allowed to just look up, secant or secant cubed, if it ever comes up on something. That is something you do not have to rederive that from scratch. So you can look this up in a table, back of your book, your notes, online, whatever. This should be the natural log absolute value of secant x plus tangent x between 0 and pi over 4. So natural log, the secant of pi over 4 plus the tangent of pi over 4 minus the natural log of the secant of 0 plus the tangent of 0. The secant is just 1 over cosine, so the cosine of pi over 4 is root 2 over 2. So the secant of pi over 4 would be the reciprocal of whatever the cosine of pi over 4 is. So cosine of pi over 4 is root 2 over 2, so this would be 2 over root 2, plus tangent of pi over 4 is 1, minus the natural log of secant of 0, which is 1 divided by the cosine of 0. Cosine of 0 is 1, so 1 over 1 is 1, plus the tangent of 0. Tangent of 0 is, of course, 0. So it looks like, well, this term here, the inside is just 1, and the natural log of 1 is 0. So this whole term is 0. And then here you can just leave it written as that. You can simplify it. Whatever you want to do, doesn't really matter, but I'll just write it like this. And there you have it.